Section: Introduction. In this section, we discuss the recent progress in large language models, LLMs, and their impact on natural language processing tasks. These models have shown impressive capabilities, often outperforming humans in various tasks. However, there is ongoing debate among researchers about whether LLMs truly understand the content they generate or if they simply memorize and repeat information. Some have referred to LLMs as stochastic parrots, suggesting they lack genuine comprehension. Despite this concern, we note that there have been no quantitative studies to confirm the stochastic parrot phenomenon in LLMs. While some research indicates that LLMs struggle with specific challenging tasks, they do not provide controlled evidence of understanding. Our paper aims to fill this gap by offering quantitative evidence to support the stochastic parrot argument. To achieve this, we adopt a summative assessment approach from educational and cognitive psychology to measure LLM understanding. This involves creating tasks that assess different levels of understanding based on Bloom's taxonomy. We introduce Physico, a task focused on basic physical concepts, such as gravity, which are essential for understanding broader topics. Physico consists of two subtasks that correspond to different levels of understanding. The first subtask tests low-level understanding through natural language questions, focusing on memorization. The second subtask uses abstract representations to evaluate high-level understanding beyond mere recall. We conduct experiments with various LLMs and find two main results. First, while LLMs excel in low-level tasks, they significantly underperform compared to humans in high-level tasks, confirming the stochastic parrot phenomenon. Second, our analysis indicates that the challenges faced by LLMs stem from the complexity of deep understanding rather than the task format. Our contributions include introducing a psychology-based approach and the Physico task to measure LLM understanding. Through our experiments, we successfully validate the stochastic parrot phenomenon and highlight a significant performance gap between humans and machines in comprehension tasks. We also recognize the inherent difficulty in measuring LLM understanding. Definitions of understanding often rely on the abstract concept of meaning, making it challenging to quantify. We extend the summative assessment concept to evaluate machine understanding by designing specific tasks related to a concept and assessing the accuracy of the LLM's responses. Section Summary. In this section, we introduce a novel approach to measure the understanding of large language models, LLMs, using summative assessment, inspired by educational psychology. We develop Physico, a task that evaluates LLM's comprehension of basic physical concepts, revealing that while LLMs excel in low-level understanding, they significantly underperform compared to humans in high-level understanding, thus validating the stochastic parrot phenomenon. Section: Requirements for validity. In this section, we discuss the requirements for the validity of our evaluation approach, which relies heavily on how we design our tasks. If the questions are too simple, even a weak system might answer them correctly, leading us to mistakenly believe the system understands the concepts well. To maintain good validity, we follow key principles for task design. 1. Alignment with objectives. Our questions must relate directly to the concepts we want to evaluate and measure specific knowledge about them. 2. Different difficulty levels. We include questions of varying difficulty to ensure that the evaluation can distinguish between different systems. 3. Variety. Our questions should cover multiple aspects of understanding the concepts, including both their definitions and implications. 4. Simplicity. While not essential, simpler benchmarks can better highlight issues faced by current models, such as the stochastic parrot effect in large language models. For our task design, we draw on Bloom's taxonomy, which categorizes cognitive skills from low to high levels: remembering, understanding, applying, analyzing, evaluating, and creating. We simplify this by grouping the last four skills into high-level understanding and focusing on two levels: low-level understanding. This includes retrieving knowledge from memory and rephrasing it. High-level understanding. This involves understanding knowledge beyond just memorization. Our tasks span from applying knowledge to analyzing concepts, such as explaining a physical phenomenon or analyzing a property in a general way. We introduce the physico task, which focuses on understanding 52 physical concepts like gravity and light reflection. Our emphasis on physical concepts stems from two reasons. They are crucial for intelligent systems to interact with the world, and they allow us to control understanding levels and ensure diversity in our tasks. Each concept in physico includes both low-level and high-level subtasks. For physical concept selection, we first evaluate whether a large language model, LLM, knows our concepts by asking it to recognize them from their Wikipedia definitions. We mask synonyms and relevant entities to prevent shortcuts. Next, we assess if LLMs can identify these concepts through real-life images, selecting 100 examples that reflect the core properties of the concepts. Finally, we ask LLMs to generate descriptions of concepts, including their core properties and examples. For instance, gravity is described as a force that pulls objects with mass together, illustrated by the example of an apple falling. We evaluate the quality of these descriptions using both automatic and human metrics to measure the knowledge LLMs can recall. For high-level understanding subtasks, we present challenges that require deeper comprehension and minimize memorization effects. We utilize the abstraction and reasoning corpus, ARC, approach, using grids to represent concepts abstractly, which helps us assess the LLM's understanding of physical concepts without relying solely on text. Section Summary. In this section, we outline the requirements for ensuring the validity of our evaluation approach, emphasizing the importance of task design that aligns with learning objectives, incorporates varying difficulty levels, and reflects diverse understanding aspects. We introduce the physico task, which assesses both low-level and high-level understanding of 52 physical concepts, utilizing methods such as concept recognition from definitions and visual representations, as well as generating descriptions to evaluate the knowledge of language models. Section: The Physico Core Set. In this section, we describe the physico core set, where our first goal is to identify the essential properties or key examples of the concepts we assessed. We aim to keep our set understandable for a general audience, so we chose 52 common physical concepts typically found in high school curricula. To add variety, 5 annotators labeled different core aspects of each concept. For instance, the core aspects of gravity include the attraction between two objects, motion on a slope, falling objects, and orbital movements. Each annotator creates several pairs of abstract grid representations for each aspect, ensuring that these pairs illustrate the transformation from input to output. For example, one pair visually represents the concept of gravity, like an apple falling from a tree. This process generates 1,200 paired grid examples across the 52 concepts, resulting in 403 shot instances. We provide examples that explore the concept of gravity in more depth, such as the inverse square law and the relationship between gravity and inertia. These examples highlight the challenge of accurately identifying their true labels without a deep understanding of gravity. Next, we introduce the physico-associative set. We found that many instances in the original ARC dataset can be linked to physical concepts through association or analogy. Therefore, in our second subtask, we ask annotators to select input-output grids from ARC that evoke associations with specific physical concepts and assign these as ground truth labels. Unlike the physico core, we allow for new concepts to be included during this annotation process. The annotators reviewed 500 ARC instances to find the relevant ones, resulting in 200 instances with physical concept labels after cross-validation. This relabeling adds 15 new physical concepts. Each example in this subtask represents an abstract aspect of a concept, but may include distracting information, making it more subjective and challenging than the physico core set. We then create 4 choice tasks based on the annotated data. Each instance consists of 3 unique grid pairs as input examples, leading to 200 instances for both the physico core development and test sets, as well as 200 for the associative set. For each instance, we select 3 additional labels from our concept pool, along with the correct label, as options. We carefully avoid ambiguity in our negative sampling. For example, if gravity is the correct label, we won't include magnet as an option. In the following sections, we will conduct a series of studies on our physico tasks, organized into 6 research questions, RQs, aimed at addressing 3 hypotheses. In summary, we propose to 1. Investigate the performance differences of large language models, LLMs, on low-level versus high-level subtasks, highlighting the stochastic parrot phenomenon in their understanding of physical concepts. 2. Compare the performance of LLMs and humans on high-level subtasks to show that LLMs significantly lag behind human understanding. 3. Explore the limitations of in-context learning and supervised fine-tuning in enhancing LLMs' performance on high-level subtasks, emphasizing the inherent constraints of state-of-the-art LLMs in achieving deep comprehension. We utilize various commercial LLMs, including GPT 3.5, GPT-4, and others, as well as open-source models like Llama 3 and Mistral. We use the default settings for these models and run each experiment 3 times to calculate the average and standard deviation. We also test recent thinking models. To demonstrate the stochastic parrot phenomenon with physico, we need to confirm that LLMs can perform well on low-level understanding subtasks. Specifically, we want to know if LLMs can effectively recall and describe the definitions, core properties, and representative examples of the physical concepts in our tasks. Thus, we ask, can LLMs perform well on low-level subtasks, such as understanding the definitions of physical concepts in natural language? To answer this, we will evaluate the LLM's abilities to comprehend these definitions and generate descriptions and examples in natural language. Section Summary. In this section, we outline the creation of 2 sets, physico-core and physico-associative, which consist of annotated physical concepts and their associations, respectively. We also describe the development of classification tasks based on these sets to evaluate the performance of various LLMs on low-level and high-level understanding of physical concepts, aiming to highlight gaps in their comprehension compared to human understanding. Section Settings. In this section, we provide the standard definition of a concept based on Wikipedia, while masking its synonyms. We then ask the language models to identify the concept using a consistent 4-choice format throughout our experiments. We assess various text-only language models and calculate their accuracy. Our results show that both text-based and visual-based GPT models perform almost perfectly in recognizing physical concepts from standard text definitions and real-life images. We notice that open-source models tend to make more errors compared to closed-source models, likely due to their smaller size. Among text-based models, Mistral and Llama 3 do not perform as well as the closed-source options. Interestingly, InternVL and LLAVA perform worse than the open-source GPT models. This discrepancy may arise because our text definitions come from Wikipedia, which is often part of the training data for open-source models, while some images we selected may not have been included in the training data for InternVL and LLAVA, preventing them from recognizing those visual examples. We evaluate the descriptions generated by the language models for each concept. Evaluating text generation is generally challenging, especially since each concept has multiple correct examples. Existing automatic metrics like BLEU and Meteor are not effective in measuring quality in our case, so we primarily rely on human evaluation. We also propose an automatic metric through a self-play game, which we detail in the appendix. For human evaluation, we ask annotators to assess the quality of the generated descriptions using binary scores. A description receives a score of 0 if it contains any factual errors or unfaithful examples, and a score of 1 otherwise. Our results, shown in a table, indicate that there are no factual errors in the generated descriptions, except for Mistral, confirming that our selected concepts are based on fundamental and widely accepted knowledge. While the open-source models are generally accurate, they sometimes include correct but less common facts, such as mentioning single-slit diffraction as an example of wave interference. The additional self-play results in the appendix further support that all models can accurately recognize concepts from their own descriptions. Overall, this suggests that the models can generate correct and sufficient information. We also asked annotators of our core set to evaluate whether the core properties they annotated are included in the generated descriptions. This measures the recall of the descriptions regarding core properties from PhysicoCore. The recall rates for GPT 3.5 and GPT 4 are 85.0 and 90.0, respectively. However, some exceptional examples from PhysicoCore are missed in the descriptions. For instance, the models fail to connect the movable pulley with the lever concept. Upon manually reviewing these missed properties, we found that most could be recalled if we prompted the models again with any more core properties or examples. This indicates that the models are aware of and can recall the core properties of concepts in PhysicoCore, even if they do not always generate them with the highest probability. In our experiments on high-level subtasks, we address research questions about our understanding subtasks. For RQ2, we investigate whether humans can understand the abstract representations. We ask 3 independent annotators, who were not involved in our task design, to perform the same classification task as the language models, using the same inputs. They are allowed to consult GPT-4 for definitions of unclear concepts, particularly for the core test set. The results show that our tasks are largely solvable for individuals with a college-level education, with humans achieving over 90% accuracy on the PhysicoCore tasks. The physico-associative tasks are more challenging and subjective, as annotations depend on individual perspectives. Despite this, humans achieve an average accuracy of 77.8% on these tasks. We further investigate human performance on a subset of physico-associative tasks, where participants annotate instances they believe do not have adequate explanations among the 4 candidate answers. We find a 10.4% disagreement rate, and on these disputed examples, human accuracy drops to 33.3%, which significantly contributes to the decline in overall human performance. Section Summary. In this section, we evaluate the performance of various LLMs in recognizing physical concepts from standard definitions and images, finding that closed-source models outperform open-source ones, particularly in generating accurate descriptions. We also assess human understanding of these concepts, revealing that individuals with college-level education achieve over 90% accuracy on core tasks, while facing more challenges in associative tasks, resulting in a notable accuracy of 77.8%. Section: Stochastic Parrots on LLMs. In this section, we discuss the concept of stochastic parrots, which was first introduced in a pioneering study that questioned the understanding capabilities of large language models, LLMs. This term has gained significant attention, with many papers across various fields referencing it. Despite its recognition, we note that there is a lack of quantitative experiments to validate this concept, which motivates our research. We also explore the Abstract Reasoning Challenge, ARC, which tests inductive reasoning in a few-shot context and serves as a benchmark for LLM intelligence. Recent studies have focused on enhancing LLM performance on ARC. We draw inspiration from ARC by using input-output grids as abstract representations in our task design. However, our approach differs significantly. We emphasize understanding the transformation rules between inputs and outputs and their connection to physical concepts, specifically to assess the stochastic parrot phenomenon. Furthermore, we highlight recent efforts to create tasks that challenge LLM understanding. For instance, a humor understanding task has shown a notable performance gap between LLMs and humans. Our contribution lies in providing a quantitative experiment to verify the stochastic parrot phenomenon in LLMs through carefully paired low-level and high-level tasks.